when we start looking at stoichiometry, we have to look at mole ratios because stoichiometry is the study of us taking quantity of one substance and comparing it to the quantity of another one, right? If we say we start with 10 grams of our reactant, how much product can we get out, right? We have two different substances. But we can't compare our substances gram to gram, right? If I have 1 gram of hydrogen, think about that's equal to a mole, right? 1 gram of hydrogen would be the same as 1 mole of hydrogen. But 1 gram of oxygen, is that 1 mole of oxygen? No, it's a 16th of a mole, right? So we can't compare grams of substances from one to another because they don't represent the same quantities. So we have to compare things in moles. And so that's why we have to use what's called the mole ratio step. When we look at mole ratios, it's a conversion factor that allows us to compare any two substances or amounts of substances. Okay, but our substances have to be in moles. Sorry. Okay, so all the mole ratio step does is allow us to compare two different substances. In the mole ratio step in our stoichiometry problems, which I'll show you here in just a little bit, in our mole ratio step, that's the only time in which the moles doesn't get the 1. Okay, that's the only time within our stoichiometry steps or our T-chart that the mole doesn't always get the 1. And I'll look at what that means here in a second. But when we start comparing moles of one to moles of another, we might say, what's our mole ratio step between potassium chlorate and oxygen? What would it be? What's my mole ratio between potassium chlorate and oxygen? Just 2 to 3, right? We take the moles from the coefficient in front, right? Because this reads, right, this chemical reaction reads 2 potassium chlorate moles, when it decomposes, breaks into 2 potassium chloride moles and 3 oxygen moles, right? 3 moles of oxygen. So when we look at mole ratio steps, we're looking at the coefficients right in front of them, okay? That's what we need to be paying attention to. This is where we get our numbers for our mole ratio step in the stoichiometry calculation, which we'll talk about in just a little bit. But we need to know that those mole numbers come directly from the coefficient. Okay. So we're going to convert, we're going to start with basic stoichiometry conversions between moles of one substance to moles of another. Okay, moles of one to moles of another. So go ahead and write down the balance reaction, and then I've got a question underneath that we'll start working through together. Okay, I already balanced the reaction for you. And then I've got the question listed. Our stoichiometry calculations are going to fit into our T-chart method, right? That's how we do stoichiometry calculations. And so with any kind of T-chart method, we always start with what we know, right? So I'm going to start my T-chart with 5 moles of CO2. Okay? And my goal is to go from moles of CO2, because that's what I'm starting with, to what do I want to end up in? Moles of lithium hydroxide, right? So I sometimes even like to say, I'm starting with 5 moles, and then I'm going to hear how many moles of that, right? I kind of like to even put that above the reaction, so it really focuses me in on what's my mole ratio, which one am I looking at, all that kind of stuff, okay? But my goal is to go from moles of CO2 to moles of lithium hydroxide. As with any T-chart, what we want to get rid of has to go diagonal there. Moles of CO2. And then this is the only time we can do this, but we can go moles of lithium hydroxide here. Okay? This step right here is called the mole ratio step. The only section of our T-chart where we can have 2 different substances has to be moles to moles. Okay, that's it. We cannot have grams of lithium hydroxide and moles of carbon dioxide. It doesn't work that way. We have to make sure that if we have two different substances in the same column of our T-chart, it's got to be moles to moles, right? That step right there is called the mole ratio step. Okay, this one right in the middle is called mole ratio. Okay, and so where we get those numbers from, they don't just get ones, right? That wouldn't do us any good. Where they come from is we look at how many moles of CO2 are in our reaction, and there's just one. And then how many moles of lithium hydroxide? There's 2. And so now I cancel that. I'm left with moles of LiOH, which is what I want. That means I would need 10 moles of LiOH. Right? Pretty simple. That should be pretty straightforward, I think, for us to see, especially with this one because we had really nice, pretty round numbers. And we could have done this without the T-chart, I really think, right? If we started with 5 moles when we were only supposed to have 1, that should automatically tell you that if we need the ratio to be 2 to 1, this should have automatically been 10. Right? Can you see that how that works out just with nice, pretty round numbers? We don't get nice, pretty round numbers all that often. But when we do, it makes it easy. Okay? Let's try, I think I have one here that I'll let you do on your own. How many moles of O2 will result from the decomposition of 0.66 moles of hydrogen peroxide? So first you have to balance, then you go with the mole conversion. Okay, so go ahead and try that one on your own. Are you guys doing okay on the balancing, or are you stuck? So if you're stuck, see how this side has 3 oxygens? This is the lone one out, right? This side could never have an odd number of oxygens, right? Because it's O2. So no matter what coefficient you put there, it's going to be even. So this is your odd one out. So start with that one to make it even. So I put a 2 there, which makes this 4, makes my oxygens 2 plus 2 more, so 4. And so now we've got an easy fix on the left side to make both of those 4. Where did these numbers come from right here? Right, they came from balanced equations, so they come from the coefficients in front of our compounds. All right, very good. Let's look at the next step of that. Using moles and grams. Okay, this is where we take our amount of substance in moles and we convert our other substance to grams or vice versa, right? Or we can do either way, okay? There we go. So here's our formula. As you get that question written down, we'll just go ahead and balance it. We don't need to waste time doing that right now. Okay, I think this is right balance-wise. 6 carbons there, 6 carbons here, 12 hydrogens there, 12 hydrogens here. 12 oxygens plus 6 is 18, so 6 plus 12 is 18, okay? So balanced, but it says what mass in grams of glucose is produced when 6.4 moles of water reacts with carbon dioxide? Okay, so we start with what we know. 6.4 moles of H2O. Right, we're starting with 6.4 moles, and we want to know grams. Right, we want to know grams of glucose. So I'd continue my T-chart with moles of H2O. And what do I have to go to next? Do I go right to grams of glucose next? I need to go moles of glucose. Moles of C6H12O6. And I go into my mole ratio step there, right? Into my mole ratio step. So 6 and 1. And then all I have to do is add onto my T-chart. Right now, if I stopped, I would be in moles of glucose. But I want to be in grams. So I go moles to grams of C6H12O6. We go back in that part of it to moles getting the 1. Right? And then I look for how many grams are in 1 mole. So there needs to be molar mass.
180.
Thank you. 180 grams per mole. Any questions about how that chart got set up? Okay, when you do the math, you multiply across the whole top, divide by the whole bottom. Oh, we got 192? Okay. Good. Okay. So I gave you a balanced equation here. You're starting with moles and going to grams, similarly to what we just did previously.
Me too.
83.2 grams of O2. Okay, good. Questions with that? What would happen if we asked for, if we started in grams and were asked to go to moles, right? What if this said grams and this said moles, right? We'd do it a little bit different, right? I would go 3.12 grams of water. I'd go grams of H2O, moles of H2O, and then I would go moles of H2O to moles of oxygen, and then I would stop, right? If it asked it backwards, we're still only doing 3 steps, right, or 3 sections to your T-chart, but you would do the grams part first, and you would end with the mole ratio. We just want to make sure we're careful about what do we want to end up with. That should be the unit that's right here in our T-chart, right? The one we want to stop with, we wanted, if in this question it asked for moles, that's what needs to be there, okay? So you'll also notice that nowhere in here did we use Avogadro's number, right? Nowhere in the question did it mention molecules or atoms, and nowhere did we use Avogadro's number. So that's really important. Sometimes people, I think, because they don't know what else to do, they put it in there, and it doesn't apply, right? It doesn't need to be there. So just something to think about. Okay. Now we're going to go gram to gram. So this is where we go all 4 steps, right? We start in grams, we end in grams. What's kind of the natural progression? If we have to go through this of grams of one substance to grams of another, walk me through what does the progression have to be? Grams of one to moles of that to moles of the other, or mole ratio, and then grams of our last one. Good. All right, how many grams of water? Do you want to try this one on your own? Okay, why don't you try this on your own?
To check and see if that is like accurate.
I guess the only other way would be to write it backwards, right? Start with 37 grams of this, rerun your molar mass, and check and run it backwards.
No way to like.
Now, the only way to think about it is to see if it's reasonable, right? We started with more than 1 mole, and then you have to look at the mole ratio to see if that, I mean, so there's not like a real quick check method. No. The only thing that would help is that you double check your units to make sure you didn't flip-flop one of them along the way. But not something, no, there's not really a check for that. And so we're going to eventually get into something that's called a limiting reactant. Did we do that at all last year? Okay, I didn't think so. Okay, the limiting reactant is something that, one of the reactants is going to run out first, right? Very rarely in chemical reactions do we dump in exactly the right amount of both, right? There's going to be one that gets used up first. And that's called a limiting reactant, right? It's limiting the thing. But the excess just tells us that's the one that's left over. So eventually that will come into play with how we solve problems, but right now that doesn't affect anything. Yeah, good question. Okay. Let's do this one. I have this, you're going to balance it, and then there's 3 questions, kind of one of each type. Okay? One of each type. Go ahead and get the equation and the question written down. I'll balance it, and then we'll start looking at how it works, okay? But let's think about a couple things before you even start. If I'm just converting molecules to molecules, will I ever use a molar mass in this one? No, right? If it never says grams or if it never asks for mass, we don't use molar mass. So just something that you need to be careful with, okay? Oh, you guys are welcome for balancing that for you. It's like one, two minutes. It was a lot easier than the last time. I hope I did it right. I guess we'll see.
Yeah, I was gonna say that was pretty quick.
I hope it's right. For these ones, you're going to have to write pretty small. Your teacher is going to be big, right? All right, remember, what's this NA stand for? Avogadro's number, right? It's just so I don't have to write it out every single time, right? I just put it in there so I don't have to write out 6.022 every single time. When we do molecule-to-molecule conversions, I hope you see that there's a major shortcut, right? In terms of what we have to actually plug into our calculator, there's a pretty major shortcut because we have Avogadro's number on the top and on the bottom. Right, so if we have it on the top and the bottom, we don't have to plug in our calculator, right? Because those are going to cancel. We don't need to multiply by it when we're just going to turn around and divide by it. So when we're looking, I'm just going to take 1.21 times 10 to the 24th times 2. Right, so we did a lot of work to just realize that, oh, it would be twice as much. Okay?
Oh, wait, so we don't have, we can just do times 2. And
Yeah.
Okay.
Right. Because since Avogadro's number is on the top and the bottom, we don't have to bother plugging it in.
Okay. AC plus BD. Is that right?
Close, very close.
BD plus, but that's just what I said.
Yeah, but it's okay. You're close.
BC plus AD or AD plus BC.
AD plus BC, but almost. Because here's the issue. When we look at any compound, we build them with the cation, then the anion. Cation, then the anion, right? And so when these things combine, we'll see the cation and the anion combine and switch places. So we would have AD, which you were right, but the second thing is it would be CB,
okay.
right? That's because the cation has to be listed first in our chemical compound, okay? So we see these ions switch places. In a double displacement reaction, when you put them together, everything splits apart, becomes its own ion, and then reforms with a different partner, right? Reforms with a different one. So those are the types of reactions that we will build and balance and work from, right? These are the types of questions that you can start to think about with me, is that I'm going to give you a starting amount. You're going to have to build and balance the reaction, and then we'll do a stoichiometry problem with it, right? So it has all the parts to it. Okay, so first things first, it asks to build a reaction with potassium nitrate reacts with magnesium fluoride to create what, right? Let's build and balance that, and then we'll answer the question that goes with it. Okay, so I'm going to get rid of that stuff. Did you guys get this formula up here? Okay, I'm going to get rid of that. All right, potassium nitrate, KNO3 plus, then make sure you leave some space to balance it. Magnesium fluoride is MgF, just MgF. Why don't you grab your periodic table of ions out? MgF2, right, because magnesium is a +2. All right, so it will yield, or it would produce two different things. First of which is going to be, right, the outsides come together. So K and F. Is it going to be this, KF2? No, right? This is really important. When you build and balance, the subscripts here don't go with them. Okay, they don't necessarily go with them. They might, but they don't go with them. What happens is we have to look at potassium and fluoride together, right? Potassium's +1, fluoride is -1, so they would just go together KF. Okay? And then the insides come together, magnesium and nitrate. So that would be Mg. Mg is +2, and NO3 is -1. So when we crisscross that, it would be Mg parentheses NO3 parentheses 2. Right? Do we see how we did that? Not so much? Okay? So look at, when we know that these insides have to come together, we know that magnesium and nitrate need to form a new compound. So then we look at them individually. Magnesium's charge is +2, nitrate is -1, so we crisscross those down. That's where we get the parentheses and the 2 from. All right? And magnesium still gets the 1 here. But ours is not balanced yet. All we did was put the reactants and products in place. We still have to balance them. So we've got 2 nitrates here, which means we need 2 there. That makes 2 potassiums. So I think that should be good, right? Okay, a way that I did that quickly without my list was I started with nitrate, right? Nitrate stays together on both sides. So if I know I've got 2 nitrates here, I have to have 2 over here.
But technically you don't have to do that.
You don't have to. You can do nitrogen by itself and you can do oxygen by itself. Doing the polyatomic ions as the whole just saves you some time because you got one less thing.
Yeah.
But since nitrate is on both sides, I did it with just nitrate. So since that made 2 potassiums, I had to bounce back and change my potassiums on this side. That gave me 2 fluorine, so I needed to look on this side, and that was right. Okay, so it's often this bounce back and forth one way to the other. Why don't you guys go ahead and do the stoichiometry problem that goes with it? Molar masses look good? Okay.